All right. Howdy. So today I'd like to introduce our speaker, Jianquing. If you're not familiar, he is one of the most famous statisticians alive today, and he's done a lot of work on a lot of topics. So he actually had so many accomplishments that I'm not going to be able to list them all here, but I'd like to give a small survey of some of the things that he's done. So he's currently the Frederick L. Miller Professor of Finance, a Professor of Statistics, and the Professor of Operations Research and Financial Engineering at Princeton University, where he was the chair of the department from 2012 through 2015. He is a recipient of the COPS Award, the Morningside Gold Medal for Applied Mathematics, a Guggenheim Fellow, the Tao Lu Shu Prize, the Guy Medal in Silver, a Nether Distinguished Scholar, and a LeCam Award recipient. He has co-authored 4 highly regarded books on statistics and econometrics, and has authored or co-authored over 300 articles on finance, economics, statistical machine learning, computational biology, and many other topics. He's been consistently ranked as a top 10 highly cited mathematical scientist, and I actually checked this morning, he has over 85,000 citations on Google Scholar. So chances are you probably cited him in something. He's a joint editor at JASA and was previously the co-editor-in-chief of Animals and Statistics, Probability Theory and Related Fields, the Journal of Econometrics, and many other journals. He's also served on the editorial boards of JASA, Annals of Statistics, Econometrica, and many other boards. He's also served on many scientific advisory boards to many different institutions, such as the Institute of Economics, Academia Sinica, the Institute of Mathematical Sciences, and Peking University. He has many research interests, as I said, including data science, machine learning, finance, economics, computational biology, and I'm very excited to see what he has for us today. So let's welcome our speaker.
Thank you, Charles, for a very nice and kind introduction. That reminded me, like 6, 7 years ago at UIUC, he as a student, he always had a very strong leadership. So my talk today is on ranking inference based on top choices and multiple comparisons. So it's really like a statistical problem in the, modern like data age time. So it's really we just starting on the field. There's a lot of data of this kind, and this is really based on the joint work with my former students and postdocs. Zipanos, he was my postdoc at the time. In Jianquing a couple of years ago, and in particular, I want to mention Maxine. So she is really an outstanding student. Will be on the market next year. She read 10 papers on methodology of different topics with me at Princeton, and continue on with biostatistics and the causal inference at UPenn as a postdoc fellow. Anyway, so I will talk about introduction, model and uncertainty, quantification, ranking inferences, numerical studies, and the conclusion. So this is, let me begin with introduction. So ranking data play really an important role in many applications, right? So when you search for the web, they give you page rank, right? Voting, ratings, right? Recommendation systems, product design, sports competition. Even believe it or not, if I have a time at the very last slides, I offer some of my thoughts on referencing system, particularly for the machine learning conferences, right, where there's over 10,000 of submissions being made each time, and all of these can be based on partial ranking, like we were asking to do a few papers, right? So we already put a rank on that. And here is one examples of ranking, right? So I thank Ray for inviting me here. Matt Wong, I think, composed the number of publications by statistician, and he gave like 5 or 6 top journals because of space. I only pick 3. Like so you can rank by number of publication or like the preference scores. Clearly, Peter Hall is the winner. He was also the interviewee. Ray certainly far ahead of me, and just as B and so on. Right? So all of these really is a rank based on preference scores, right? Now, what is my contribution today is really talking about uncertainty in the rank, right? So it's you can always based on some statistic and rank, right? So where is uncertainty? Right? In publication process, we may refer in process is uncertainty. There's some kind of uncertainty in that, right? So similar that apply to the university ranking or currently QS ranking, right? So we usually use like a ranking based on some kind of preference scores, and then just display the uncertainty, display the ranking. I know that the US and the world reports itself understand there's uncertainty in the ranking, so therefore they do like a 5 years, which is far more. Stable, less stable than, let's say, 25 years averages. Right? So certainly there's uncertainty in the displayed rank. Now, my question today is how do I quantify the uncertainty or do I count this interval for the displayed rank, right? So, and in particular, you may ask, right, is school A better than school B based on your finite amount of data you have available? Right, similarly, you can ask, is school C among top 20 universities, right? And then you ask yourself, someone like you ask yourself, how many schools I need to apply so that with 95% confidence that the top 5 is all within my application list. Right? So this will be all those kind of uncertainty. And when we talk about the ranks, right? So it's always involved with all unknown scores. Right? So if I want to ask how, let's say, Texas A&M is ranked, it involves everybody else, right? So in the system. So therefore, we contribute to the high-dimensional statistical inference. So in other words, when I do it, I can not only talk about one university's score confidence interval, I have to talk about 4,000 universities inference, right? And in addition, the number available to us, the data available to us is typically limited, particularly when we compare about heterogeneity in the data process. So what is the related literature? There's a lot of related literature based on pairwise comparisons. So the picture that I draw here is really just like a tennis tennis sport competition. Right? So it's like for those two people on each dot here, the node here is really an individual player, and if they ever match each other, we draw an edge. Right? So this forms a graph. So this comparison graph is relatively sparse compared with all pairwise possible comparisons. So there's a number of studies on this. Typically, is on estimation what are the fundamental limits fundamental limits on the estimation of the preference scores. Now, of course, there are multiple. There are also multiple, let's say, MA comparisons. If I choose the 3 products, I ask you which one you prefer. Right, and or you ask you to rank the movie, let's say in Netflix competition, but you use 3 movies, ask you what is top 1, what is top 2, what is top 3, right? So some people maybe give you 4 movies, ask you to give a complete rank 1, 2, 3, 4. So the reference on multiple comparisons are relatively sparse. Now talking about the rank inference to even more sparse, right? So there's only a few papers that we are aware of, and most of those papers only based on pairwise comparisons. So that is just like a tennis case. You either have a match or you never match, right? And the method being given before our work certainly is suboptimal. We'll see how they do bond for maybe adjustment in order to make simultaneous confidence intervals so that you can talk about rank. Okay, so in order to answer the uncertainty in the uncertainty, that's a model, and this is really a popular model people have. So let me begin with the setting. Let's imagine that you Imagine that there are n items that you can sell, or n products, or n music, or n movies, right? So I pick n at random. Let's say pick three items at random and ask you, say, which one you prefer. So you only observe the top choice and then you leave. So this is the based on partial data, right? So for example, if I offer you three products, I know which one you buy. I don't know your second choice or your third choice. And even the top choice is more certain, right? Similarly, if I give you a website, through the website, you choose you click the choice and you leave, right? So this is the data I have. And I assume that we do this n times. So again, for simplicity, we are using the same. I have n products. I do this n times. So every time you know that which product being chosen and choices. Okay. So this is the setting, and I now assume that each product have intrinsic score, or each individual have intrinsic ability. So I denote this by third I. The third I is the one I want to learn. What is the intrinsic preference score for a particular movie, or a particular book, or a particular music, right? So this is the third I. So I have n items, so therefore I have n scores. So now what is the outcome, right? So for let's say n items under comparison. So for each these n items under comparison, each one has each one has preference score theta I. Right? So the theta I is the preference score. The chance of winning is proportional to the preference score, and this is under the loose axiom of choice. So under this assumption that if you do additional product doesn't change the preference of choice, then the model had to follow something like this. So this is really a linguistic model. So the assumption I do is like follows, right? So if I choose a product, I ask, let's say, 10 person, 10 in this case, I mean L. I use L, I observe L times to rate those products. So therefore, I got the multinomial outcomes, right? Percentage of people like the first product, the percent of people like the second product, and percent of people like the third product, right? And the probability of winning is proportional to the intrinsic score or preference score of that particular product. So in this particular case, I only assume that you observe the top choice. Every time I give you three products, you tell me that what is the top choice. Okay, if you give me a full ranking, you can apply to our case too. So I just didn't talk here, but you can apply to our methods too. So this is called packet loose model. So this a little bit fast, but let me recapture again. Just imagine it's just a new kind of ranking problem. Every time I give you a three product, this is M, right? So and if these three products being compared in terms of graph theory, just like the edge I showed you before, I say belong to have an edge connection. So has an edge connection. And the ones being drawn, I ask three part being drawn, I ask 10 people, L person to rate. So at the end of the day, I got the empirical preference winning probability. I assume these winning probability follow the multinomial distribution, given the multinomial distribution with the probability like this. So what is the learning objective? Right? So our learning objective is to learn the preference score theta I of each individual product, and use the uncertain quantification of this, right? So once you do uncertain quantification of each preference scores, you create the movie very easily, and we can maybe even ask whether the first and the rank 2 has any statistical difference in terms of preference score. And so the first one we are going to do, and the second one we are going to learn to do is ranking inference. I mean, is really, let's say, breakfast at Tiffany, rank number 5. What is the confidence interval from 3 to 8, or what the confidence interval? And in particular, if n equal to 2, we are back to the BTL model. That is, every time when there's a match, you observe the probability of success, meaning what percentage. Right? So, and this is the problem. So now, if you need to estimate the preference score of n individuals of n movies, the first thing you think is the maximum likelihood estimator. Right? So you starting from the most powerful statistical results and maximum likelihood estimator. So given that n item being compared, so I'm using graph theory, meaning there has an edge connection between these hypergraph connection between these n persons. Right, so given these groups being compared, so then I observe these are the sufficient statistics, right? So the proportion of women is the sufficient statistics. And they follow multinomial distribution. This is really just a multinomial likelihood. In computer science language, they call cross entropy, right? So it's really just multinomial likelihood. And this is really the likelihood function that I have. So now for simplicity in my presentation later on, since I bring the graph theory, that helped me a little bit, right? So since I bring the graph theory, hypergraph, I say, well, two nodes are being connected, or it's probably P, the probably link is P, just for us to understand. Now, of course, I can put everybody preference score by adding 5 more points or less than 5 more points, just like in the class, right? So you give everybody 5 additional points, doesn't change the ranking. So we have identifiability issues here. So it's really identifiable up to a constant shift, right? For this reason, just like in most statistical application, I'm going to set a constraint that the average mean score, average preference score is equal to 0, so that I have fully identified model. So our problem seems pretty simple. We just have high dimensional, n-dimensional parameters, and whenever they're being picked, the observed data for multinomial distribution, so you can really write down the likelihood like this. Now, the challenge is how can we analyze this optimally, and what is the new idea that I can give you to give a confidence interval for individual scores as well as for the rank. So here is the first results. And so I'll explain a bit. So first, let's talk about radar convergence. So again, P is the probability of a connected edge. Thinking if you think you have difficult imagine hypergraph, but thinking of the usual graph, right? So two node being connected with probability P. Then basically say if P is a little bit bigger than this order, then the maximum likelihood estimator has L2 average rate of convergence is at this rate. I'll explain why it's like that, right? The L infinity means the maximum error, right? So the maximum component-wise estimation error rather than average error is a little bit bigger log n times this, right? So if we, the implication of this basically is this, right? So the error is not concentrated on any individual entries, right? So the error is uniformly spread across all n items. That's why the average error and the maximum error is approximately the same, right? And if you ask me why the radar convergence looks like this or like this, you can easily imagine. Right? So our sampling scheme is like this, right? If you choose 3 items, like they're being compared, you observe women. And if you choose another 3 items, you observe who are the women person. Right? So now, if you want to estimate the accuracy or estimating the ability, my individual ability, right? So I have to be under the comparison, right? So now, how many times that involve me, right? So first of all, because I choose an item, I'm already there, so that I have n-1 person need to be chosen from n-1. And the chance these people being chosen under our model is P, and the ones being chosen, I will compare we match our time. So this is the sample size. Right? So in other words, the rates that you see here is really the square root n. Right? Or if I take the square root here, is the square root of the sample size. So that's why I rate it like this, because if you want to talk about the accuracy of my, I mean, the accuracy of the ability, I had to be involved with the match. And what the person involved me is this is the combinatorial, and this is probably that predicted group being chosen. And when being chosen, we compare outcome. So this is really the sample size. Okay, so this is and in particular, of course, is n equal to right? So we are talking about pairwise comparison. The classical BCL model, then the rate is reduced to some of our previous work too. So now here is a few technological advances in terms, at least in terms of information theoretical bounds. So previously, there are similar work on these multiple comparisons, and they require P is an order of magnitude bigger than S, and our P is really just this order, log n divided by this, so it's much smaller. And now the information lower bound is really like this. And you may ask why this is information lower bound. This has been studied in graph theory. So if I were able to, let's say, do pairwise, if I were able to rank all items, right? So my graph must be connected. If my graph is disconnected, then two groups or three groups will never be compare each other. There's no way which one is better, right? So graph, in order for a graph to be connected, it has been studied in, let's say, Erdős random graph or in hypergraph. P had to be big than this. So this is why our method is information theoretical optimal. You cannot really reduce the sampling complexity further. This is the minimum that you can get. Okay, now as a result, since we were able to get L infinity long, that is the maximum estimation error, right? So if I were talking about what is the top five, let's say, items. So with the top five items, so if the top five K item and top K plus one, the fifth and sixth one has big enough gap. The gap is bigger than my statistical error, then I could be with 100% confident recover the top five items. And this is really the result. Really just a translate of what we said. What we said before. We have maximum L infinity error that we talked moments ago. We have this L infinity error. So long as this L infinity error is smaller than the signal, that the gap between kth item and k plus one item's preference score, then we can fully recover it. And this is just a statement that just translate that theorem. So we can recover top k items. Now, the more challenging one is high-dimensional inference. So unlike classical where we have less than 3 parameters or finite number of parameters, so now I have n parameters, right? So and under the minimum sampling scheme, so it's a little bit more challenging. But nevertheless, the heuristic is very similar, right? So if I let just like the partial what they call profile likelihood similitude like that, right? So if I like to say that m is the parameter without involving the m item is the item that I wanted to inference. And this is the associated likelihood. Then, associated likelihood that involve theta m. And it's very easy to write because this is multinomial distribution, so I could easily write it down. So if I take relative of this function, of my likelihood function with respect to the nth parameter, because the multinomial, people already seen this looks like a very multinomial likelihood. You can analytically write it down, and is indeed a somewhat independent random variable, like a Bernoulli trial in hypergraph. Similarly, we can do as what usually we do, like the second derivative, right? So the second derivative involve like the curvature of Fisher related to Fisher information there. And then we just do the usual like the Taylor expansion at heuristic level, the theta at the difference between your estimated one and the true one. We learn from mathematical statistics when we take first class PhD classes. So it's more or less like the first derivative divided by the second derivative. So everything is fine. So what makes difficult in high dimensional is this. So this guy is a random variable. So how can I replace this random variable? There's an n-1 item here. By is associated true parameters, and similarly, the second derivative by is associated true parameters. This involves a lot of new technical arguments that we need to do, but nevertheless, we were able to show that that approximation hold and the technique we rely on is also called Lee-Wang-out argument. Now, it is pretty popular in mathematical arguments. Lee-Wang-out is very popular for estimating cross validation, for estimation, some kind of like prediction errors. But Lee-Wang-out also nowadays being very popularly used as a technical tool to deconvolve the complex dependence. But anyway, so we basically showing that this results hold, the approximation I say hold, with the approximation error that can be uniformly bounded. So this is the first part. Now, once this approximation hold, then we can easily derive the asymptotic normality, very much similar to the traditional one that we use. So this is really just a asymptotic normality for each individual items. And this one is pretty much the same as your multinomial, when you evaluate the true parameter, pretty multinomial Fisher information, pretty much like that. So this is, so you can establish the asymptotic normality. So now if I compare the result to the existing ones, also we are under much less technical assumptions. So previous one, there's a work by one of my former students, now is a Harvard statistician. So he assumed that L is generally, L is very large, had to be n squares. But there are other literature like n equal to 2, that is pairwise comparison. You really just L need to be a finite number. And this is more or less assumption. And then we really, our result really say this hold for any number comparison, two-way comparison, three-way comparison, or general comparison that all hold. And similarly, in terms of sampling complexity, how dense the graph is, how sparse the graph is. So the previous one required that P is pretty big, and our case P is much smaller. So this is in terms of the technical assumption, we have much weaker results. Now I think these are more on classical. You just need a new technical new model to do. Now is a new thing. So how do I do rank inference? Right. So as I said before, the rank inference really involve all items. Right. So you may ask yourself, top two items mean really statistically different in terms of rank, right? Or in terms of score function. So what is the less than 95% confidence interval for the rank of this particular meeting, right? So this kind of question is what we are asking. And here is a few questions that we can ask further, right? So how do I build simultaneously confidence interval for the rank of, let's say, 5 products or 3 movies, right? So this is the simultaneous confidence interval of the rank is even more ambitious, right? So maybe I ask myself, is an item, let's say, refer as Stephanie, among top 10 movies, right? So with 95% confidence, right? So this is the second question that I'm asking. And then you may say, well, how do I select a set of top 10 items with high confidence? So in other words, how many products I need to include so that the top 5 products are all there? So all these involve, whenever you talk about rank, it's involve all unknown score. So we need simultaneous confidence, right? And we need a framework. And this framework actually it is not that difficult if you think of this, if you fully understand this graph, right? So let's say, suppose for example, let's take one item. That M item, let's say is Texas A&M, right? This university as an item. Right, so in order to get the rank of the confidence interval rank of the Texas A&M, I need that university, the university compared with all other universities. Right? So this is the case university. So I need a simultaneous confidence interval for all. I mean, all the simultaneous confidence interval for all the comparison, like Texas A&M compared with another university, Texas A&M compared with another university. I need a simultaneous confidence interval. Suppose I were able to do that, right? So there's a lower bound and upper bound in the preference score. Suppose I were able to control lower bound and upper bound, so I have confidence on that. So now let me just display these confidence intervals here, right? So if I display here, let's say on this side, so the confidence interval doesn't touch zero, right? So that means these universes have higher preference score than A&M. So in other words, your ranking is worse, so my rank would be 1, 2, 3. So the best rank I have would be number 4, because these three I have high confidence better than me. Similarly, like on this side, so all those upper bound is less than 0, right? Upper bound is less than 0, that means Texas A&M is ranked above these universities, so I can counting from bottom up, right? So this would be, so this, if I translate this would be the counting number of the lower confidence limited than 0 plus 1 is my lower bound. I mean, lower bound of the rank. The rank, the smaller the better, right? So this is why counting a little bit weird. And then this one is just counting from n. So this is how we translate the rank into, I mean, so confidence, the preference score, simultaneous confidence interval into the rank, right? Because rank is a discrete random variable, so it's very difficult to give precise probability to have 95% coverage. I can use the preference score simultaneous confidence interval, and now I just translate that into the rank that I got this, right? Now the next issue is, how do I construct simultaneous confidence interval? And this is the standard statistical methodology, right? So so since I'm going to compare the kth item and the nth item, right? So this we observe the difference between two preference score, and this is the true or expected difference between the two units true score. And then because both of those have asymptotic normality, so all you really need to do is talk about binomial distributions, pairwise probability, and these are nearly independent because I have n items there. So divide by the standard error. So I need to construct the maximum of construct the distribution of these maximum deviations, right? So the observed different and the expected different divided by this, right? So this, when I talk about maximum random variables, this is already become a different distribution, right? Even though each individual is normal, but then when you take maximum, it becomes complicated. Now, adding to the complication, I'm not only, yeah.
I'm sorry, on the previous slide, does that mean that it seems to be your confidence interval lower bound, upper bound, and one point of the increase?
Right. So the lower bound is increasing with respect to alpha.
Respect
Uh,
rank. So you have each rank has a confidence interval around it. Does it preserve rank or the lower and upper bound of this?
Right. So in other words, all I'm saying is this: this confidence interval, will have at least 1 minus alpha coverage probability if I started from here, right? So let's say if I were able to construct simultaneous confidence interval for pairwise for comparisons with this theta n is given to you. So if I have this, then I just translate this set into the rank. So my rank had to be bounded on this event. My rank had to be bound between these two numbers. Is that? But anyway, so if I have a question, we can discuss further. Okay, so this is the study I want, and I not only want to do a rank for one movie, I want to do a rank for a set of movies, right? So I'm going to take a maximum again over the set. Now this is really the simultaneous complex interval I want to build. So this is highly complex random variables, but to give a distribution is relatively challenging, but we can always rely on some kind of like a bootstrap counterpart, right? So by the realization that we had before, so the all these data J's, right, can be written if you go back to what we have here. So all those have a kind of Taylor expansion like this. And then when you have L items, the numerator is near the summation over L items. So if you have coming from here, you can really write into a form that we would like to have. And this data is very explicitly written out over there. And then we just do the also called the multiplier bootstrap. So we multiply that another random variable here. So now this is the condition on data. This is a random with respect to the created another random variables. So this G distribution, now the question is this G distribution approximate the distribution I want here. So, and this is really some kind of very kind of theoretical work. We actually show that this is indeed the case. The quantile coming from our bootstrap, and this is the random variable I want. They are approximated quite well. So this is really the theoretical part. And because this there's a set M here, right? So the width here also depending on M, so it has adaptive width with respect to M. And now if I translate the simultaneous confidence interval in terms of pairwise comparison among all items into the rank, I will get the simultaneous rank for each individual item. If you give me multiple items, if you give me like multiple items, I can do this too, because this is just a translate of lower bound and upper bound from what I was talking before, because we just need the simultaneous confidence interval based on this, whether the difference covers zero or not cover zero. So this is really the interval that we have. So now if we compare with what is our method compared with the previous, right? So the previous result by for BTL, and then Chao and his collaborators propose also 1 minus alpha confidence intervals. However, the 1 minus alpha confidence interval, when we're talking about, let's say, the simultaneous confidence interval, I want to talk here in this step. Simultaneous confidence interval among all those cases. So there is really a bond familiar adjustment. And as a result, they're using based on Gaussian approximation and bond familiar adjustment. As a result, the multiple would be an order magnitude, right? So the confidence interval would be an order magnitude wider than our methods. And in addition, the way they do it, you can only rank for individual movie. You cannot simultaneously rank for 3 movies, right? So then that cannot be that. And also our method, the way we construct, you can also apply to one-sided confidence interval. Right? Before I was talking about two-sided, but we can really translate it into one-sided confidence interval. So once we are able to do one-sided confidence interval, we can do hypothesis testing, right? So whether a particular product has a rank or better rank smaller than K, or has a rank big than K, and then you can also just do like the usual, just say, hey, if you are lower than big than K, you reject. The similar way when you translate one-sided confidence interval into one-sided hypothesis testing, and then we could say the following. So the about test will be approximate control at the level alpha, because the way that we do is control, so have size alpha. And in addition, when the difference is sufficiently apart, and you have power 1. This is the same as what we say the consistent estimation of top K items. So this is the result that we get. And similarly, if you want to say, hey, can I find a confidence interval, or can I find a set of movies so that the top 5 movies are all in my set, right, with high probability. So in this case, you can also do that because we were able to construct the rank on one side confidence interval. Right? So if I construct one side confidence interval for all items, and all I really need to see is how many of those rank lower than K, right? Means rank better than K, right? So if the first item rank better than K, I say, well, I should pick on this I hat, right? So if the second item is not, then it's not in my set. If the third item is ranked better than K, is on my set. So if once is the lower bound is smaller, means better than K, then I will have this. Okay. So this is really the way that we construct. And now let me just quickly illustrate this by another example, just to so that we get a better idea what we are doing. So in this particular example, I have n equal to 60, n equal to 3. I have every time I pick 3 items, and once 3 items being picked, I ask 20 person to compare them. In my simulation example, I assume, let's say, the I star is uniformly distributed on this range. And now I talk about the L2 error of these 60 items, yeah? And then this is the probability, how often you sample the data. So what is really the sample complexity that we have here. And if we draw this, right, the statistical error against our rates of convergence, right, it appears very linear, right? So this also showing that our rate result matches with our theoretical results. And this is similar things. This is similar for our implicit norms. And at the same time, we also try different kind of n's and different kind of L, means number of comparison on 3 items being chosen. And this is the probability center. So these are showing that asymptotic normality all holds, not only their holds, but also the standard error being estimated, the standard deviation being estimated also matching with the empirical data. And we also use it to construct some smaller confidence interval for a few items. So in this particular case, I take item number 10. Right? So, and this is like if you estimate item number 10's score, I think the coverage probably is right. So if you are estimating item number 10's rank, of course, it's always a conservative rank. So therefore, you have 100% coverage probability. But the risk that we have here is just about half of the previous method by Gaussian and John's methods. So, and the main reason is that we do not do Gonfalonian adjustment, but we actually calculate the complex joint distribution. And this is just one of those numerical examples to illustrate. So in that particular case, we are making 100 jokes from this many users in that Jasper data case. And for illustrating purposes, in this particular example, I have n equal to 100 jokes, right? Every time I sample 3 items at random, and 3 items being sampled with probably like 0.05. And then once the 3 items being picked, we ask 80 person to rate, and they tell you which one is the top ranked joke. So based on this data, I was able to estimate all the scores for all the scores for each individual jokes. So it happened to be number 89 has the highest theta I star, right? So number 50 joke is the second highest, and so on. Right? So we can also construct confidence intervals based on this. Right? So number 1 typically is rank number 1 and 2 is very normal. Let's say look at number 10. Our interval maybe say is between 8 and 12. 8 and 12, and then this is also our method. So this is the method based on the Gonfalonian adjustment, which have much wider, right? So 4 to 16, and so on. And we can also do one-sided confidence interval. What is the best rank a particular given mean has, and so on. So we can all do this kind of analysis. And then we also try different kind of, you could pick 3 items, could be 4 items, could be 6 items. And so we do all those kind of thing and making intervals. So because of the time, let me also skip this, but let me quickly summarize what we have talked so far. Right? So we start with multi-rate comparison with observing top choice. You only know where the top product being picked. And this is a very natural way to extend the classical two-way comparisons, a PTL model and modified PL model and rate. Right? So this is based on 2 items. This is based on complete ranking. We only have observed top item. And we propose the next likelihood estimation of scores and establish the L2 rate and L rate of convergence. We derive the linear expansion as well as asymptotic normalities of each items. And then we introduce a new inference framework of the item, because those items are random items are discrete random variables. So we use simultaneous confidence interval scores and then translate this into the rank. And we also verify all those results with asymptotic normality and the numerical experiments. And there's a lot of extension I can talk because due to the time, I just skip, right? Let me just say one possible application. If someone has energy and pushing it, it'd be very interesting. So like in 2020, NIRPS also has this many submission. In 2023, we all have lots of submissions, right? So this is put a lot of burden on the system and the program reviewers. We heard people say, asking high school students to review some of those papers, right? So there's a lot of individual analysis, right? And but many referees usually, usually like review multiple papers, right? Let's say I review 5 papers. So therefore, I have complete ranking on those 5 papers because I give different scores, or I could be just have more confidence give 3 among those rankings I have, right? So now, so if you think with the same than what we have, if you draw average among papers that have ever been compared, you really will a kind of hypergraph. So therefore, you can estimate the each paper's preference scores, right? Just based on those pairwise comparisons. And this kind of idea can really reduce a lot of referring, per paper. Really, you just need, technically speaking, you just really need one referee review one paper. That's enough because there's sufficiently number of people also referring other papers, multiple papers. And this could lead to really a better design of the refereeing systems. Currently, we get involved part of design of how to improve, let's say, the refereeing mechanism of these like machine learning conferences, particularly like in Jesu of Pennsylvania. So he's using like a mechanism design based on author provided preference scores, but that preference scores is useful, but then still they are subject to manipulation. So if we are thinking of like just like the same as when we talk about product preferences, every time we refer 3 papers, you really do rank of those 3 papers already. I just use your rank. Based on many other referees multiple compare on the papers. At the end of the day, you could estimate, say that K, the same way I'm talking about here, and that can reduce just each paper being referred only by one qualified person rather than a lot of unqualified persons. So with this, I know the time is up. Thank you very much.
Thank you for that very fantastic talk. We have lots of time for questions.
Yeah.
The bound P and L were playing similar roles. What is the intuition behind that?
In and out.
Most of the bounds you had lower bounds.
Okay. Yeah, so it's totally different. This is good question. So basically, again, is a similar question that we asked a moment ago. Again, is like this, right? So I Sorry. Oh, okay, no, this, I did this. Okay, okay. Okay, so it's like this, right? So because I give some, let's say n is fixed, let's say the third item is fixed. So I contrast simultaneous confidence interval for pairwise comparison with the third item. And once I do that comparison, I get the lower bound, right? So it's is bigger than zero, like the picture I draw here. So it's basically saying that these three items has higher higher preference scores. So therefore, when I count my rank, my best rank is 1, 2, 3. Right, my best is location here 4. So therefore, I'm counting this way, right? The upper bound bigger than zero. I know there's a notation issues here. And then the other one, lower bound bigger than zero, is meaning these items are better. That's why I counting rank this way. Now, this side basically saying that my upper bound is less than zero, and then this is notation issue looks very similar, but actually is the upper bound less than zero. So then must be these items, I'm confident my score is higher, right? So therefore I'm better, so I'm counting rank. My rank is counting from the bottom, right? So from n, so this why the formula looks like this, yeah. So you are counting how many items you are sure is better than you, how many you are sure worse than you, and all those ambiguous in between is where your rank is. Yeah. Yeah.
What do you think the real data set, the big M is not fixed? Say
Okay.
some users have rated 5 movies, some users have rated 10 movies.
That's actually very good question. So this is exactly the part where in my extension I probably didn't mention like that. So the same way, let's say if I do product design or do even the Netflix competition at that one, somebody was given 3 movies, somebody was given 4 movies. And the same way, like when I click the website, sometimes they present me 5 websites, sometimes you present me 3 websites, right? So you can, and let's say suppose you do this and you observe the top choices, then the result can be extended. The likelihood under that model can be written, and the result can be extended. And in that particular case, we find that using like a spectral method, so we create a kind of like covariance matrix based on these kind of ranking, can be helped to solve this like a more complex problem with a heterogeneous number of items and also heterogeneous number of comparisons. So this is actually a follow-up work that we were working to, yeah. Yeah.
How does the model handle ties?
Very good question. So in our particular case here, right, so to study, we didn't really assume there's a tie, like we assume BLT model. Yeah, so that would be a very good one. We haven't extended that yet. There's a lot of application. Actually, one of my students is very interesting. She went to Google Eat. And also later on become Google Brain, also Uber Eat and Google Brain, and actually she's at Stanford Business School Marketing. So she was asking further, right? So how about individual ranking difference, like your preference and my preference also has some kind of heterogeneity, and also each of us have covariance. So there are a lot of possible extensions, including you say ties. So we just as a first, just like we're talking about mean regression, mean without doing regression yet. Right? So the question you ask is very important. We do not have a particular way of handling tie yet, but there's a lot of extensions. So that's why I will mentioning this and hope some people who have interest get into market design. That may be a good issue to talk about, that like heterogeneous preferences and ties, all those practical issue arises. But very good question, yeah.
All right, well, let's thank our speaker again.
All right, thank you.